Hello, everyone. Welcome again to our webinar series of researchers in heritage science organized by the interdisciplinary thematic platform of SESİK PTI-PAIS. I'm Duygu Ergenç. I'm a Ramon Kakal Fellow at Institute of Geosciences, and I'm part of the dissemination working group of this thematic platform. As most of you know, PTI-PAIS is focused on heritage science, and among its objectives is the dissemination and the transfer of all the results of the groups that make it up. That's why we encourage you to participate in these initiatives, which aim to continue holding one webinar a month on different topics, which you can also propose. Today, we have the pleasure of having Bobo Jia from China, who is going to talk about from microstructure to conservation, understanding hydrosalt mechanical deterioration in earthen heritage sites. Bobo Jia is a research assistant at the Institute of Archaeology at Cultural Heritage in Lanzhou University, and she holds a PhD in civil engineering, again from the Lanzhou University in China, and the joint PhD in geotechnics from l'École nationale des ponts et Sauget in France. Her research focuses on the microstructural evolution and coupled hydrosalt mechanical behavior of earthen heritage materials under climate-related stressors. These include extreme snowfall and rainfall, intense evaporation, and drought-driven over-irrigation, which accelerate phase transitions of sodium sulfate and sodium chloride, and threaten the outdoor preservation of the Great Wall. Her work also addresses tourism-induced humidity fluctuations affecting earthen plasters at the Mogou grottos, where hygroscopic sodium chloride plays a critical role in material deterioration. This presentation provides an overview of salt weathering processes and their relationship with the geotechnical context of earthen heritage sites in China. It presents key outcomes from her PhD research and discusses perspectives on mitigating salt-induced damage in cultural heritage through integrated, multi-scale, and multidisciplinary processes. So, Bobo, you have 45 minutes for your presentation, and then we will move on to Q&A session to questions. I would like to remind to those attending during the presentation, if your camera and microphones are active, please deactivate them. Once Bobo finishes her presentation, I'll pass on the questions you have written in the chat. And thank you very much to all the attendants, and especially to you, Bobo, for being with us today. I'll pass on word on to you. The screen is yours. You can share your screen.
Okay, thank you, Dugu. Um, Hello everyone, I'm Bobo Jia, and I'm very happy to have this chance to now it's okay. I'm Bobo Jia from China, and it's very nice to meet you here. And I'm very happy and honored to have the chance to share my research on salt deterioration in earthen heritage sites in China and their conservations. And I would also like your organization and your participation. Today, I will present my work on microstructure evolution of salt-affected soils, like in the coupled hydrosalt mechanical behavior carried out during my 2-year visiting PhD at Laboratoire Navaillé, École nationale des ponts et chaussées in France, and also my PhD research at Lanzhou University in China, focusing on the mitigating salt damage by regulating the hydraulic properties of repair soils. First of all, let's have a look at my research focus. Overall, my work on earthen heritage sites is mainly along the Silk Road, especially the Great Wall. Especially the Great Wall and across the northern China and the Mogao grottos in Dunhuang, which are located in the arid and semi-arid regions. And the Silk Road was a network of the trade routes connecting Asia and Europe, active from the 2nd century BC to around the 15th century. Now I'm here in Lanzhou and in Dunhuang, close to the eastern starting point. And if we follow the road, it reaches in Valencia. So I think this is quite amazing, and it makes me feel a little bit closer to you. So originally, these routes were used for silk export, but later they expanded to many other goods, including the products from Europe, such as wine. And over time, the Silk Roads enabled not only trade, but also the exchange of culture and art. And many heritage sites developed along these routes. So in general, the dry climates in these regions is favorable for the preservation of the outdoor heritage sites. And this is also why many of these sites have survived until today. And the first is about the Mogao grottos. So now, how about walking into the Dunhuang Mogao grottos in Dunhuang? And okay. Thanks to the digital Dunhuang team from the Dunhuang Academy, we can have the immersive visit to several caves. For better preservation, some of these caves are not open to the public, but now we have the chance to see them. Sorry, that the guides now is only in Chinese, but that's why we can just follow the arrows and move your mouse to change the view. For example, we can let's first look at the paintings around the walls, the wall facades, and there are also the sculptures made of clay. And if we move a little bit closer, we can have a more detailed view. And then we look up, we can have the settings called zaojing in Chinese. These are placed at the top of the cave, often in the squares or circles, creating the impression of an infinite scaled sky. I think it's quite similar to the dome paintings in cathedrals, although the zaojing in Mogao is mainly decorative, while I think the cathedral dome has a structural function. And here, we can also have other caves. We can look at one or two together, and then you can try by yourself after the seminar. So here we can look at the cave of 254. And according to the UNESCO, there are more than 700 caves at the Mogao grottos with about 45,000 square meters of the mirrors and more than 2,000 sculptures. Now we can get into these caves. In this cave, there is a group of sculptures at the center. In the past, people would walk around it in the circle and while praying, like cycle around. And if we meet a little bit closer, we can see that the earthen plasters beneath the painting layers, which is my research focus. This is made of clay and plant fibers, and it has a typical layered structure that is supports a coarse layer, a fine layer, and then the painting layer. And there is another, and you look around, there is a list that you can have a tour, online tour at the Mogao grottos that you can discover later. So now let's go back to the reality. You may also notice that some paintings are fading or disappearing. In fact, thousands of years preservation is already a miracle, but we hope to make it last even longer. First of all, we need to recognize that the paintings are deteriorating. Among the different factors, salts are often the most important, and about 200 caves show clear salt damage, and the relatively low humidity is generally good for preservation. However, the caves are small and enclosed and with limited windows, so when many visitors enter and stayed for a long time, combined with a trend towards warmer and more humid conditions, the humidity inside can increase from around 20% to as high as 16%. As a result, salts from the material itself and from the foundation migrates to the surface and accumulates there, and repeated crystallization and dissolution cycles gradually alter the pore structure of the earthen plaster and eventually lead to the visible damage. At Mogul, the most common salts are sodium sulfate and sodium chloride. Sodium sulfate is particularly damaging because it can undergo large volume expansion, typically around 3 times during hydration, and this makes it one of the most destructive sources of porous earthen plasters. As shown in the first row of figures, the surface becomes loose, which can lead to the detachment of the painting layer. And the sodium chloride shows much smaller volume change. However, it is highly hygroscopic, meaning it can absorb moisture from the air, so it remains a serious threat to the painting inside the caps. Here you can see the typical salt spores caused by sodium chloride. And for the outdoor earthen heritage sites in this region, such as the Great Wall, salt deterioration also poses a serious threat. Here we can see the distribution of the Great Wall, which was also listed as a UNESCO World Heritage Site in 1987. It extends for more than 21,000 kilometers along these red lines crossing 3 main climate zones in China. It starts from the arid and semi-arid in the north, begins here, typical saline and alkaline regions in China, and also my main research area, and extend to a more humid of the humid eastern regions. And in some areas, the wall is surrounded by farmland. Why? Because to support the larger populations and the wide extent of the Great Wall, this situation is quite common. In some cases, over-irrigation often occurs due to low rainfall and high evaporation. This further accelerates the upward migration and accumulation of salts from the foundation to the facades and leading to a more severe basal erosion. So this slide shows a typical progressive deterioration right? What? Sorry. This slide shows a typical progressive deterioration process driven by salt in arid and semi-arid regions. The earthen wall was mainly constructed using local loess, compacted in layers. These structures are relatively stable under dry conditions, but they are sensitive to moisture. Although rainfall is infrequent, it can be intense and is often followed by strong evaporation. And after rainfall, this leads to a repeat wet-dry cycles and thus repeated salt crystallization at the surface as the water evaporates. This leads to the repeated wet-drying cycles and thus repeated salt crystallization and expansion, followed by dissolution and shrinkage within the structure. Over time, this process loosens the material and weakens the integrity of the heritage body. And once the soil becomes loose, wind-carrying sand particles can further accelerate the erosion. Because the wall was built layer by layer, so it is prone to detachment between layers, leading to the basal erosion and even potential structural collapse. This process can become even more severe when combined with earthquakes or dynamic loading, such as vibrations induced by the trains. And arriving at this point, we know that water and the salt behavior within the pore structure of earthen heritage materials can progressively deteriorate the size. So in my research, I try to understand this process from microstructure evolution to macroscopic behavior from a geotechnical perspective based on unsaturated soil mechanics. These figures show the soil water retention curve, SWRC, or some people also call it SWCC. Whatever the as SWRC describes the relationship between the water content of the soil and suction, or in other words, the capacity of the soil to retain water during drying. So for an initially saturated soil, suction is low and mainly controlled by capillary effects. At the early stage of drying, the change in water content and suction is small. Once the suction reaches the air entry value, air starts to enter the pores to replace the water, and the water content decreases rapidly. This is the transition zone. With further drying, the soil reaches the absorption-dominated zone, where only a small amount of water remains, but suction becomes very high. And from the capillary theory, suction is related to the pore size. Smaller pores generate higher suction. So during drying, water in larger pores dries first, followed by smaller pores. So in this framework, what is the role of salts? And for soil, for loess, which contains clay minerals, drying usually leads to the shrinkage, making the structure denser. However, when salts crystallize within the pores, especially the sodium sulfates, they can expand and disturb the structure. So there is a competition between shrinkage and crystallization-induced expansion. And the dissolved salts generate osmotic suction, especially the sodium chloride, which can enhance the water retention. And rather, when salts crystallize, they may act as a bonding agent, increase stiffness, or induce micro cracks depending on the conditions. So overall, water retention, volume change, and microstructure evolution together control the macroscopic behavior and mechanical properties of the material. So linking the microstructure to hydromechanical behavior is very important because it helps us better understand the deterioration process of these heritage soils to build a reliable framework between the microstructure and the hydraulic behavior. Now we can have to the experimental part. Since the larger scale sampling from the heritage sites is not allowed, in this study, we used the substitute soils from Loess Plateau in northwestern China and Limon de Plateau in northern France. These soils have geotechnical properties similar to those of the sand soils obtained by microsampling from a collapsed section of the Great Wall, so they can be considered as representative materials. And due to the COVID-related restrictions at that time, the main material used in section 2 was the loess from France, and the experimental was carried out at Laboratoire Navier. And after the characterization, we concluded that both the reference soil and the tested soil are classified as low plasticity clay, that is CL in the USCS system. However, they are dominated by silt. So in practice, they can be described as silty clays. And now we can have an overall look at the experimental framework. And the samples were prepared using the double-sided static compaction at a rate of 0.5 millimeter per minute. We obtained the homogeneous specimens with a height of 20 millimeter and a diameter of 50 millimeter, a dry density of 1.565, and initial water content of 17%. After preparation, different drying conditions were applied. For the microstructure analysis, we considered 2 drying modes and 5 salt conditions. As mentioned before, clay shrinkage during soil drying can lead to the microstructure evolution, but we aim to evaluate the effect of salt on the microstructure. So in the slow drying mode, the samples were placed on a suspended setup and dried under controlled temperature and humidity conditions for half an hour, then sealed for 3 hours before the next drying cycle. And during each drying, the samples were inverted up and down to ensure more homogeneous drying. This process was repeated until the target water contents were reached, namely about 14, 11, 9, 7, 5, 4, 3. And based on the pretest, this range of the water contents can represent the soil water retention curve, and the drying time of 13 minutes and sealing time of 3 hours were also determined through pre-test, in which different conditions were compared, including 15, 13, 16, and 19 of drying, with and without inversion, with and without sealing. So the results showed that a half an hour of drying under this slow drying mode, shrinkage cracks can be effectively avoided. Therefore, the microstructure evolution in this group can be mainly attributed. Mechanical data correspond to the same.
I think there's a connection problem. Huh. Okay. You are muted, Bob. Hmm.
So to make better use of the samples and to ensure that the micro, hydro, and mechanical data correspond to the same conditions, the test followed the procedures described below. And in addition, the triplicate samples were prepared to ensure the reliability of the data and to control the experimental variations. And at each target water content, the samples were sealed with the filter paper and placed in a controlled cooling room for at least 2 weeks to achieve equilibrium. At equilibrium, the soil and the filter paper share the same suction. Using a well-established relationship, the metric suction of the soil can then be determined. And the parallel samples were cut into 4 parts. Top, bottom, sides, and center, and each part was further divided into small blocks of about 3 millimeters for subsequent tests, including total suction measurements using a hygrometer based on the Kelvin equation and the electronic conductivity to represent the salt distribution, and the mercury intrusion porosimetry MIP for pore distribution, and the scanning and SEM for the morphology and elemental analysis. And we also considered that some verifying pores cannot be accessed by mercury intrusion, so the water ratio obtained from the MIP is theoretically smaller than the actual value. So therefore, we used a volume displacement method based on the Archimedes principle to obtain the global water ratio to calibrate the MIP data. And in addition, the non-destructive X-ray CT imaging provides the three-dimensional pore structure information with a resolution of 10 micrometers. In this study, it can also extend the pore size distribution beyond the range of MIP. And to investigate the microscopic mechanical response, Bender element tests and unconfined compressive strengths were conducted. The Bender element is also a non-destructive method that provides P wave and S wave velocities, and the S-wave velocity can be converted into the small strain shear modulus, which is relevant for evaluating the response to small vibrations, such as those induced by the train traffic in the gradual region. And the UCS test provides the compressive strength and the stress-strain relationship, allowing us to assess the evolution of cohesion associated with the microstructure changes. And the salt conditions include the sodium chloride and sodium sulfate are the common salts in this region. And based on the field observation, 2 and 3% were selected as representative values in salt-affected zones, and the C0, S0 was used as the control. And before moving to the microscale, we can have a look at the appearance of the samples to make me better understand the microscale phenomena. So the first row represents the samples after slow drying under different salt conditions, while the second row shows those after faster drying. Here, for example, the SDC0S03 represents a sample under slow drying SD without salt C0S0 at a water content of 3%. So from this comparison, we can see that under slow drying, the process is relatively homogeneous. When the water content reaches 3%, salt crystallization is present, but it remains relatively evenly distributed. And this is also supported by the EC values measured in different parts of the samples. And in contrast, under the faster drying, significant crystallization occurs at the top surface of the samples. And in some cases, such as the FDC3, detachment and SD, FDS3 detachment is already observed at the upper edge. And we can also observe that under slow drying, the samples without salt and with low sulfates content dry the fastest, followed by those with higher sulfates or moderate salt content, while the samples with the highest sodium chloride content dry the slowest. This can be explained by the fact that the salt solution have a lower vapor pressure than pure water, and making the evaporation more difficult. And at the same concentration, sodium chloride can generate higher osmotic suction, which enhance water retention. And this can be further discussed in the next section on water retention behavior. And there is also another interesting phenomena is like you can see that the drying rate about the FDC3 and SDC3 is like with a sample with the 3% of sodium chloride, it dries faster in the slow drying conditions. Why? Because we can have a picture of the figure H that there is a salt crust cover the samples, and it may slow down the evaporations. So the comparison between the fast and the slow drying is relative. The slower drying of C3 under faster drying can be explained because of the salt crust, and the crust partitionally forbids the evaporation. And from this point, we can move to the microstructure analysis. Here shows the pore size distributions and the pore fractions at different water contents for the C0, S0 sample under slow drying. We can first see that at each water content, the PSD curves from different parts of the sample almost overlap, and indicating that the pore structure is very similar throughout the sample. This is like under slow drying, the sample dries in a relatively uniform manner. And when all PSD curves during drying are plotted in the same figure, it can be observed that the pore size distribution evolves from 2 model to 3 model, and then to B model. Under faster drying, the newly formed micro pore peak is more pronounced than under slow drying. This addition peak in the micro pore range is associated with the shrinkage, and with further drying, this micro pore gradually merge, leading to the disappearance of this peak. And in this study, the pore size are divided into three groups. It's like the micropores, mesopores, and macropores, using 0.5 micrometer and 5 micrometer as threshold. The 0.5 micrometer boundary is defined based on the value between the newly formed peak and the adjacent peak observed in most PSD curves. And the 5 micrometer boundary corresponds to the value between the two dominant peak groups. So based on this classification, the pore fractions are shown in the bar chart. The black line above the bars represents the water ratio measured by the volume displacement method. We can see that total water ratio obtained from MIP is close to but slightly lower than the obtained from volume displacement, as the very fine pores may not be fully detected. And the blue line in the chart represents the water content, water volume ratio calculated from the water content and particle density. It is used to indicate how water is distributed within the pore system. For example, as the water content of 17%, the water volume falls within the macropore ranges, meaning that the water occupies pores of all sizes. As drying proceeds, the water gradually shifts towards the smaller pores. So in the and there are corresponding SEM images of the C0 S0 samples under slow and fast drying at representative water content. The first and the third columns correspond to the initial and final states, and while the middle column is 9% represent the stage at which the third peak in the micropore range first appears. And from now on, it's about the salt effect. And in the following analysis, to better highlight the effects of salt and drying, only the results from the top part of the sample will be presented, because under slow drying, all parts of the samples show very similar PSD curves, while under faster drying, the top part is most affected region during evaporation. So regarding the effects of the salt type, sodium chloride is like C2 and C3, and the sodium sulfate S2 and S3. These figures can show the post PSDC at different water content. The black and gray values correspond to the C0, S0 samples under fast and slow drying, and the blue and the green represent C2, and the orange and the yellow is S2. So for the sodium sulfate samples S2, the PSDC still follows a B model, and then to tree model, and then back to B model pattern. But a weak third peak remains at the last stage. This may be related to the strong water film seeking effect of sodium sulfates. And as a result, the tree model structure persists for a long time. And in contrast, for the sodium chloride is C2 samples, the PSDC remains the B model along the drying, and the smaller peak stays within the mesopause range. This can be attributed to the double layer compression effect of the sodium chloride. It stabilizes the pore structure and limits its evolution. So if we take C0 and C0 S0 as a reference, sodium sulfate S2 shows a similar evolution pattern, suggesting a relative limited effect on the overall microstructure. But if we instead consider the initial structure as a reference, like the initial is like C0 S0 to C0 S0, like C2 compared to the C2 and S2 compared to the S2, we can see that sodium chloride maintains a stable B model distribution, indicating a more stable pore adjustment processes. So when further examining the influence of the salt content, here we can see the C2 and C3 is like the sodium chloride content is increased. So an increase in the sodium chloride can lead to a reduction in the proportion of the macropores. And at higher water contents, the water film seeking the effect domains. And under faster drying, extensive sodium chloride crystallization at the top of the sample leads to the formation of salt crust, which reduces the differences in macropore distribution. And the parallel SEM images provide a more illustration of these changes. So for the initially compacted samples, the SDC3 with higher sodium chloride content shows stronger interparticle bonding than C2. The particle appear larger and more compact. It indicates a more pronounced aggregation effect. And when the water content decreases to 9, the structure exhibits slight shrinkage. However, the crystallization threshold has not yet been reached, so the pore structure does not change significantly. And then under the faster drying, due to the rapid and pronounced upward migration of sodium chloride, the difference in salt content at the top of samples with different initial salt contents become less distinct at certain water contents. And the influence of sodium sulfates mainly because evident at the later stage of the drying and can be understood in the 3 steps. First, at the initial stage, increasing sodium sulfate content leads to the reduction in the initial meso peak. And as the drying proceeds, the pore size continues to evolve and the size of mesopores increases, but their proportion gradually decreases. And finally, the drying mode plays an important role because under slow drying, sodium sulfate crystallization remains relatively uniform. In contrast, under faster drying, crystallization is concentrated near the top of the sample, which leads to a local increase of the macropores. Unlike the sodium chloride, sodium sulfate tends to crystallize around its own nuclei, forming clusters of salt crystals that are unevenly distributed within the soils. So the crystals also expand more during the crystallization, which can cause more noticeable damage to the soil structure. And if we look at the initial samples, we can see that the sample with higher sodium sulfate content, SDS3, appears more compact than the SDS2. And for the drying conditions on the faster drying, the higher sodium sulfate content sample, the strong crystallization effect leads to the development of large suspended cracks between the soil particles. So after the going through quite a lot of the microstructure details, and I have been emphasizing the micro hydro and the mechanical coupling. So now we can have a look at the water retention behavior. So these slides show soil water retention curves under different salt conditions. Overall, we can see that the salt enhances water retention mainly through osmotic suction. However, once crystallization occurs, the osmotic suction decreases and the metric suction curves gradually converge towards the top total suction curve. And if we compare the two salts at the same water contents at the same concentration, sodium chloride shows a stronger effect on the water retention than sodium sulfate. This difference can be explained because the sodium sulfate solutions have a lower effective enonic concentration, and then sodium sulfate exhibits a stronger hydration effect. It will influence how water is retained in the system. So if we look more closely at the behavior after the crystallization, we observe that the decrease in osmotic suction is slower in S2 than in C2. This can be attributed to the specific behavior of sodium sulfate because some hydrated phase retain water during crystallization. And in addition, the multi-step phase transitions of sodium sulfate can slow down the water release. And these two figures can show the influence of the salt content on the drying process of water retention. For the sodium sulfate samples, Before crystallization, osmotic suction plays a dominant role. Dissolved sodium chlorides enhances water retention. So samples with higher sodium chloride content exhibits stronger water retention capacity. At this stage, the effect of osmotic suction is greater than the metric suction. And after crystallization begins, sodium chloride progressively precipitates, leading to a rapid decrease in osmotic suction. As a result, the behavior becomes increasingly controlled by metric suction. And consequently, at the later stage, the sample with higher sodium chloride shows lower water retention. And if we choose the right figure about the sodium sulfate, different behavior occurs because both before and after crystallization, the metric suction plays a dominant role. The fast increase of metric suction S3 compared to the S2 together with its lower converge towards to the total suction suggests that sodium sulfate crystallization significantly modifies the pore structure and affects the water redistribution. So as a coupling of the pore size distribution and the hydraulic behavior, we can have a relationship between the pore structure and the soil water retention curves. Like, so first, the area PAIS model, which links the grain size distribution to the soil water retention curve. The basic idea is that we assume that the soil can be represented by an equivalent bundle of capillary tubes. And in this way, particle size is related to the pore size. And then using capillary theory, we can estimate the suction and reconstruct the SWRC from the grain size distribution. And then the Laplace-Washburn relation, which is used together with macro-intrusion pyrosymmetry, because in MIP, mercury is forced into the pores under pressure. Since mercury is non-wetting fluid, the applied pressure is directly related to the pore size through capillary principles. So by measuring the pressure intrusion response, we obtain the pore size distribution and then convert into the suction using the same capillary relationship. In this way, we can also derive the SWRC from the pore size distribution. So overall, these two approaches allow us to connect from grain scale to pore structure and then to hydraulic behavior. And this provides a quantitative bridge between the microstructure and the macroscopic behavior, which is basis for the experimental arrangement. So, and with these approaches, we can bring the pore size distribution and SWRC together. And at the early stage of the drying, for samples containing soluble salts, high concentration salt solutions from more stable water films between soil particles through the salt bridge effect can enhance the interparticle bonding, leading to the slower pore shrinkage and stronger water retention and the same water content. And as drying proceeds, the salt concentration increases until the crystallization begins. At this stage, two main effects can be observed. Firstly, salt crystals tend to fill larger pores, reducing the pore connectivity and limiting further water migration. At the same time, the remaining solution is drawn into the smaller pores when crystallization continues, leading to the partial filling or blockage of micropores. And then for the sodium sulfates, in particular, crystallization is associated with significant volumetric expansion. When this occurs in confined pores, it can generate local stresses and induce microcracks, which further modify both the pore structure and the pathways of water migration. And by linking these processes to SWRC, we observe that the dominant pore size corresponds well to the transition zones of the retention curve, and as they represent the more storage space for water. This indicates that capillary water content is largely controlled by the spatial distribution of the dominant pore network. And when macropores dominate, that strongly influences the overall water retention behavior. And in contrast, micropores contribute less to the total water content, which is reflected in the relatively slow, gentle slope of the corresponding segments of the SWRC. And now we can have analysis of the mechanical behavior because before going to results, we have to know that the samples are prepared under very similar conditions. So we can mainly focus on the effects of suction and salt. And if we look at the evolution during drying, some pores can be found. Firstly, as water content decreases, metric suction increases, which strengthens particle contacts and lead to an overall increase in Gmax. And before crystallization, osmotic suction and metric suction can work together to enhance the soil stiffness. And after crystallization begins, the role of salt changes. It can either strengthen interparticle bonding through precipitation, or in some cases, induce local micro cracks, which may weaken the structure. And the dry mode also plays a role because under slow drying, salt precipitation is more uniform, which helps maintain interparticle bonding and preserve Gmax. In contrast, under faster drying, especially for the S3 sample, the top part becomes noticeably looser, leading to a lower Gmax compared to the other samples. And in terms of the unconfined comprehensive strength, before drying, the samples show relatively high plasticity due to the combined effect of metric and osmotic suction. After drying, both strength and breathiness increase significantly. If we look at the influence of drying modes, differences appears. And under slow drying, salt precipitates more uniformly, which enhances interparticle bonding and increases the compressive strength. However, this is also lead to a sharper stress drop at failure, meaning higher breathiness. And the effects also depend on the salt type and content. For the C3 sample, the salt crust at the top promotes the interface, control the failure, and results in higher breathiness. And in contrast, for the S3 sample, the top structure is looser, which can locally buffer the stress. This leads to the lower breathiness, but also a reduction in comprehensive strength. So how can we apply this understanding to mitigate the salt's damage in earthen size? So the key idea is to regulate water and salt redistribution by modifying the pore structure of repair materials. We can take the Great Wall as an example because in many cases, irrigation water transports salts from the foundation into the wall, accelerating the basal erosion. And to stabilize the structure, rammed repair soils are commonly used. However, these repair materials often have different properties from the original soil, leading to poor compatibility. And in some cases, they are even much stronger than the original material, which can result in the detachment. And the difference in microstructure at the interface can promote salt accumulation for the accelerating damage. So the question is, instead of focusing not only on strength, can we better control the capillary behavior of the materials? This leads to the idea of applying capillary barrier system, which is widely used in the environmental geotechnics, but rarely considered in heritage conservation. As shown in the diagram, when water moves from a fine layer to a coarse layer, the capillary entry pressure of coarse layer is higher. As a result, water cannot easily enter the coarse layer and tends to accumulate above the interface. So in contrast, when water moves from the coarse layer to fine layer, the fine layer has a higher water retention capacity, which promotes the water migration. This can be seen in capillary pumping. So based on this, if the repair soil is designed to be coarser than the original soil, it can acts as a capillary barrier. And during evaporation, this limits the upward water migration and therefore reduce the transport of dissolved salts. And on the other hand, if the repair material is fire, it may enhance capillary pumping and accelerate water and salt movements. So the main idea is to use capillary barriers to limit water and salt transport while avoiding configurations that promote capillary pumping. So, and to explore the suitable compositions, we have designed different pore size distributions and set three groups of soil columns to monitor the water and the salt redistributions along the stem and along the heads to gauge the capillary effects. And here we can explore whether the capillary barrier concept can be used to reduce salt damage in earthen heritage, because in reality, the surface water content of gradual is usually around 0.1 and can reach about 0.25 during irrigation. So the key question is whether the water can cross the interface between the orange soil and the repair layer under these conditions. And for the structure with a fine over coarse structure, when the soil water content is below 0.25, water and salt can still pass through the interface. This means the capillary pumping occurs. It may turn into the upward migration. And in contrast, for the S group, with coarse over fine structures, the critical water content is much higher than 0.25. This means the capillary barrier is most effective, thus limiting the upward movement of the water and the salt. And this, we can also get example from the reality because the field observation reported by Cui showed that a specific soil layer exists at the base of the Great Wall in Qinghai province. This layer lacks effective capillary root pore structures and therefore does not provide pathways for salt migration from the foundation to the wall. As a result, this section of the wall has not developed significant salt damage over several countries of exposure. So to wrap up, we have seen that salt, water, and microstructure are strongly interconnected. At the pore scale, different salts lead to very different microstructure evolution. These differences then control how water is retained and redistributed, and eventually how the material responds mechanically. So what is particularly important is that these processes are not independent. The hydraulic behavior, the mechanical response, and the microstructure all evolve together during the salt crystallization and the dissolution. So, and from application points of view, this means that simply matching the original soil or increasing strength is not enough. Instead, we need to control how water and salt move through the material. This is where the capillary barrier concept becomes useful. By adjusting the pore structure, especially through the grain size design, we can regulate the water and the salt transport and reduce the risk of salt damage. So overall, the key message is controlling capillary behavior is essential for design more durable repair materials. Okay, okay, so that's all of my presentation. Thank you very much for your attention. Okay.
Thank you very much, Bobo. It's a really heavy and a very interesting presentation. Thank you very much. I'll check if there's something written in the chat box. And meanwhile, I say again to audience that they can ask. Okay. Yeah. Cristina Cabello asks that I would like to know how many replicate samples were prepared for each type to ensure significant results. And
Okay.
sorry if it was said, but I didn't catch it up, she says. Yes, in this slide.
We can see from this slide, I have prepared several parallel samples to set them to the drying processes, and there are at least 3 groups of the samples were prepared because I have to measure the water retention and the microstructure data. So there are at least triplicated. And for the sample and for the microstructure, I have more than 3 groups of samples because this is just a diagram. Because for a sample of like 2 centimeters high and 5 centimeters in diameter, this is quite a big sample for the microstructure measurements. And even I cut it in the very small blocks, there's more than 4 blocks here. So I can do the repeated analyze for the microstructure. And then the balance
Yeah.
also
And
molecule.
I think one question to this question. Then for each samples, yeah, for one of your samples, see all the experiments, or you use different samples for different experiments.
No. Uh, Imagine that maybe I have 6 samples. These 6 samples arranged at a water content of 9%, for example. And I have tag 2 to the contact field paper and another 2 to the contact field paper that's to repeat the results. And then after this test, the samples is non-destructive. So we can use these samples to do more tests. It's
Yeah, okay.
like this.
And it can
Yeah.
be ensured in that way.
Yes, and I didn't use the crystallization modifiers for heritage preservations, but I know this idea, but I haven't done this before about the crystallization modifiers. And
Um,
yes,
I
and
cannot use my cursor, but there's a second question.
yes, and the third one, um, before beyond these presentations, because here I only have the salt content of 2% and 3%. And before I have another series of tests, I have tested the salt content of 0, 0.2, 0.5, 4, 0.6, and 0.8 like this, and then 2%. And my results come out that when the salt content of sodium chloride like 0.4%, it can act as a bonding. Maybe like a cementation is indeed can enhance the mechanical properties of the sample. And then beyond this content, maybe its crystallization will destroy the sample. And for the sodium sulfates in H2SO4, maybe the threshold is 0.4%. I mean, a little bit salt is good for the soil, but beyond this threshold, they will damage the soil. So, oh, and
Bobo,
about
can you read the question as well? Because I cannot reach now. I don't know why to the chat box, but I think you can see. Can you read the
yeah,
question as well?
yes, I have a reply to the balance of salt strength in bonding and the presence of the salts can be a risk. For my silty clay, the sodium chloride below the 0.6% can help the soil, but beyond this, it starts to damage the soil. And so for the sodium sulfate, the 0.4 can help the soil, and beyond this, it's progressive damage the soil. What? And now can I go the next question?
Um, can you quit sharing? Maybe I don't know if it's
Yes.
related, but I
And
cannot see now the chat box.
If you don't,
Teresa, or
if
can
you
you
don't
see?
mind, I can read it because I have in
Okay.
front of me. Also, I would like to know by Cristina Cabello if there is any suggestion about how the barrier would be implemented in the site.
Mm. My implementation of the capillary barrier may be some specific to the Great Wall. My capillary barrier is set here during the reinforcement.
Is there a problem in my connection?
No, I think it's general. We lost her.
The Zoom from US is not very friendly to China. And about the sodium delays water retention, sodium sulfate delays water retention. No.
And now you are with the blank questions.
Can I show the water retention curve of the samples contain sodium chloride and sodium sulfate? Why is the sodium sulfate didn't contribute much to the water retention? Because for a saturated salt solution, for example, for a saturated sodium chloride solution, the osmotic suction is about 36 MPa, and for the sodium sulfates, it's about 4 MPa. So even it's dissolved, the sodium sulfate only generates limited osmotic suctions, and then the solubility of the sodium sulfate is lower. So we can see that it starts crystallize earlier, and then another reason is about during the crystallization of the sodium sulfates, we have the hydration processes. This can for example, when sodium sulfate crystallize, it turns from Na2SO4 to crystallize to the Na2SO4 point 10 H2O. So there we have 10 water here. So this is complicated hydration processes, because not like sodium sulfates, it's maybe just, although its solubility is higher, but when it starts crystallize, it's just crystallize. But for the sodium sulfates, it's crystallized, but it's maybe it have different stage of the crystallize processes, like they have 5 water, they have the hydration of 10 water, and in this hydration chemicals, it will hold the water. And I think this is maybe the reason why it can delay the water retention curve change. It's like
Yeah, she says thank you again for your explanation.
Okay.
And I would like to ask you, as far as I understood, you worked on separately on sodium chloride and sodium sulfate. Have you considered in the future maybe to work on the mixture of salt contents?
I have did it during my master's research. As a master because I didn't show in this presentation, but as you can see that the Great Wall may cover the mountains where they have the snowmelt infiltrations, and during the snowmelt infiltrations, it will cover the freeze and the thaw cycles, and it will cover the salt phase transitions. And in this context, I have designed the experimental where I have composite composition of the sodium chloride and sodium sulfate. I have, like I said, I have the sodium sulfate from 0% to 2%, and I have sodium chloride from 0% to the 2%, and then I have like 1% of sodium sulfate and plus 1% of sodium chloride and 1.6% of sulfate and 0.4 chloride, like this kind of composition. I have a paper to explain this about the water and salt redistribution and the mechanical evolution, but I didn't do much microstructure measurements.
Yeah. Okay, thank you. Thank you very much. It's a really interesting topic.
I'm sorry, because I didn't manage to have to find maybe a direct way to explain these conditions.
Do we have other questions from audience or questions or comments? Again, Cristina Cabello says thanks so much. Now I can see the chat box.
Okay. And but about
Monica Alvarez says that thank you very much for this. Is so interesting talk.
thank you. And about like the question about the strengthening effect of the salts, because in this presented study, I just consider the damage effect of the salt. So I just set the salt content of 2% and 3%. But I think yes, it's very interesting when we low down decrease the salt content, maybe we can have another phenomenon. Maybe we can have more an understanding on the water retention.
Yeah, probably. And for the wait, someone comes. For the conservation, you said that the different sand additions, no?
Additions.
So yeah, using sand into the conservation interventions.
Using sand.
Yes, if I understood well, or maybe it was because of I check your papers, but yeah, I remember that in your presentation, one point you put sand.
Oh yeah.
Huh. I would like to again maybe ask if for different salts contents and you would add different sand portions.
Yes, I have put sand because as I said about the capillary barrier and the capillary pumping,
Yeah, that's
so
part.
we have to modify the grain size compositions of the materials to prepare the coarse soil and the fine soil. And for the fine soil, I put kaolin, and for the coarse soil, I put sand.
Augusti Sala Luis says that thank you so much to you for presentation.
And thank you for your attention.
If we don't have more questions or comments, we can conclude, I think.
Yeah.
Thank you everyone for attending, and thank you again, Bobo, for
Thank you.
your presentation. Very interesting presentation. Ruth Lowe says thank you very much. Very nice presentation.
Thank you.
And see you in the
Thank you.
next presentation.
Yes. Bye bye.
Bye bye. Ciao.